Hola, hi, this is Al, your statistics and probability instructor. Let's get to work. In this video, I would like to discuss with you some of the properties of the expected value of a random variable. As usual, we're going to use an example to introduce some of these properties. So, consider the following situation. So you own a mobile phone store. You have two locations, one of them at the local mall and another one downtown. Okay, now let's define the random variables that we are going to be studying, the random variables that we are interested in. So let x represent the number of phones that you sell during the next month at the mall location. Okay. On the other hand, we define another random variable, y, and this one represents a similar quantity, the number of phones, but the ones that you sell at the other location, at the downtown location. Make sense? Okay, so now, based on your experience, we are going to have the following probability distribution for x. Okay, let me write it down. Probability distribution of x. As you already know, when we use this term, probability distribution of a random variable, what we're just saying is we're going to give you a table with all the possible values of the random variable x with the corresponding probabilities of assuming those values. Make sense? So either a table or an expression that gives you that. The list of all possible outcomes with the corresponding probabilities. Make sense? Okay. So, on one hand, we have phones sold, and on the other hand, we have probabilities. So based on your experience, these are the possible outcomes: 200, 300, and 400, right? And the corresponding probabilities are for 200, 0.4 or 40% of that scenario occurring. We have the same probability for 300, and finally we must have 0.2 for the last possible outcome, 400. Now let me just remind you about the properties of a legit probability distribution. These numbers, each of them, must be a number between 0 and 1, and when you add them all up, you should end up with a 1. So we're good, right? That's a legit probability distribution. Now we are going to have something similar for y. Okay, let me try and recycle this. Now we're going to have a y. Probability distribution of y, the other location. So for that one, we have 100 as a possible outcome, and the probability of that result is 0.3. We have 200 as a possible value for the random variable y, but that probability is different. We have 300 for that location too, but the probability of seeing that is different. And finally, for 400, we have 0.05. Make sense? Okay, so now the questions that we would like to answer. We want to find the expected value of x and the expected value of y. And we would also like to find the expected value of the profit. Okay? Of profit at the mall and downtown. Make sense? Okay. So, solution. Let's try to let's try to answer those questions. So, first, let's find this, the expected value of x. And again, let me remind you that x is a random variable that represents the number of phones sold during the next month at the mall location. Okay? So this would be the typical number of phones sold at that location, right? First, by definition, the expected value of x is just what? You guys remember? Remember that it's going to be the sum of the following product possible value times its corresponding probability, right? So in this case, let's go back to where we have the probability distribution of x. So applying the definition for expected value would be 200 times 0.4 plus 300 times 0.4 plus 400 times 0.2. That's it, right? Just again applying the definition. So 200 times 0.4 plus 300 times 0.4 plus 400 times 0.2, right? Okay, so 200 times 0.4, that would be 80, plus 300 times 0.4, that's 120, and finally 400 times 0.2, right? That's the same as 80, right? You guys agree? Yeah. So 200 times 0.4. Yeah, that's 80. Right? 300 times 0.4, 120. 400 times 0.2, 80. Right? So what we have here is 280 total. Right? No problem. Okay, so now let's find the expected value of y in a similar way. Right? Again, we're going to be using the definition, and then that's it. So by definition, expected value of y equals, now we have to refer to the probability distribution of y. So it would be 100 times 0.3 plus 200 times 0.5 plus 300 times 0.15 plus 400 times 0.05. Make sense? Okay, so let's write it down. 100 times 0.3 plus 200 times 0.5 plus 300 times 0.15 plus 400 times 0.05. Make sense? Let me just check that I got the right values. 100.3, 200.5, 300.15, 400.05. Okay. So now let's find that. Let's find those products. So it's going to be 30. It's going to be 100. Right, 300 times 0.15, that would be 45, right? And finally 400 times 0.05, that would be 20. Okay. So that's the same as 130 plus 65, that is 195, right? 195. Okay, so we're done with part A, right? Now let's do part B. Let me just here say that that would be part A. Okay, now let's proceed and do part B. So if you remember, right, from the statement of our problem, if you will, what we want to do is to find the expected profit in each location, right? Okay. So now let's see what we have here, right? Okay, so something that I forgot to tell you is that it turns out that the profit is different at each location, right? So what I forgot to tell you is that in the case of the mall location, you're going to have a profit of $25 per phone. Okay? And then it turns out also that the profit at the downtown location is $35 per phone. Okay, so let me write that down. So it turns out that, let me use M for the profit at the mall location. And that profit happens to be $25 per phone. Since the number of phones is represented by X, then that's what we have, right? Let me write it down here. Okay. So let's find it. Okay, let's find the expected value of the profit at this particular location. So as you can imagine from what we did in part A, well, we're going to apply the definition again. Okay, but to apply the definition, what we need to find first is the probability distribution of M, right? So let me write that down. Probability distribution of M. Okay, so just like before, right? By probability distribution, what we mean is either a formula or a table where we have the possible values for the random variable with the corresponding probabilities for those values. Okay, so let me use lowercase m to refer to a possible value for the random variable, uppercase M that represents the profit at the mall location. Let me use this to refer to the probability of seeing that value. Okay, so since this variable is 25 times x, we have to go back and see the probability distribution of x. So for x we have 3 possible values, 200, 300, and 400. And then M is defined as a number, $25 per each phone sold. So it's going to be 25 times 200. That's a possible outcome. The other one would be 25 times 300. The other one would be 25 times 400. So we are going to have 5,000, 7,000, 500, and finally 10,000. You agree? Let's write that down here. 5,000. We're going to need more room here. Great. We have 7,500 and finally 10,000. Okay. Okay. Now, what's the probability of a profit of 5,000? Well, you are going to have a profit of 5,000 if the first value of x occurs, which means that that is going to happen with probability 0.4. Make sense? Same thing is going to happen with this guy. You are going to have a profit of 7,500 if you sell 300 phones, and that is going to happen with probability 0.4. Same goes for the last value for the profit. 10,000 happens with probability 0.2. Make sense? So we have 0.4, 0.4, and 0.2. Point 4, point 4, and 0.2. Okay. So now that we have the probability distribution for m, right, we can find the expected value easily. So by definition, expected value of m equals, remember, just the possible value times its probability of occurring, 0.4. So 7,500 times 0.4 plus 10,000 times 0.2. Okay. So that happens to be just, you know, these products are going to be easily found. But let me just point something out, and this is the reason why I wanted to discuss this example. Okay, so be patient with me. Instead of just directly computing these products, I'm going to make an observation here. I'm going to say, hey, note that this is the same as 25 times 200. That 5,000 is the same as 25 times 200 times 0.4. Plus, this 7,500 is the same as 25 times 300. Okay? And finally, that 10,000 is just 25 times 400. You agree? And then we realize that 25 is a common factor. We just factor that out. And then what we have here is, let me just be a bit lazy here. I'm going to copy and paste this. And I'm going to get rid of the 25s here. You guys agree? That's the same. But what I want you to note also is that, hey, see this expression inside those square brackets? Well, that expression happens to be something that we have seen before. Is this guy the expected value of x? So we plug in that. So this is the same as 25 times the expected value of x. And then, oh, okay, we already have the expected value of x, which is just 280, right? Make sense? And then, well, we can find that easily. So 25 times 280, there we are. Make sense? Got it? Okay. So, anyway, now that you have seen this, let me tell you what would be the profit at the downtown location, right? We're going to define something in a similar way, right? Now we're going to be defining a new random variable. I'm going to be calling it D. That is going to represent profit at the downtown location. Okay? Let me copy and paste this. Let D be profit at the downtown location. And now it turns out that at the downtown location, well, it's 35 times y. Okay? So how about we do it? As a homework problem, you could try and do this step by step, like we did here. Okay? You find the distribution of D, that's what we called our new random variable, and then just like before, for M, use the definition. But what I would like to do now is being lazy. Just use our observation, right? So if the expected value of M was 25 times the expected value of X, chances are, and that's something that you will have to verify using the definition, the expected value of D, it makes sense that it will be 35 times the expected value of Y, which we have already found. So this would be 35 times expected value of Y, and the expected value of Y is 195. Let's find it. So 35 times 195, 35 times 195, that's it, 6,825. Okay, make sense? Okay, so homework, you're going to verify that. Check this. Check this using definition. Okay, so first you're going to find the probability distribution of D, then you apply the definition, and you are going to verify that that number is the correct one. Okay? Okay. Let's summarize what we did here. So, what we realized here is this. Hey, I had an original random variable x, and I defined a new random variable. I called it m in this case, which looks like this: a constant times our original, our old random variable. And when computing the expected value, what we realize is that the expected value of m is that constant, that 25, times the expected value of x. You will be verifying that for a different value of that constant, for 35. Okay? So anyway, that's the take-home message. Let me write it down like this. Let y be a generic random variable with expected value. Let me use in probability and statistics, we love using Greek letters. So to refer to the expected value, to the mean of our random variable, we're going to be using a lowercase Greek m, a mu. Okay? And to be super specific, let me add a subscript here. Oh, that's a mean of that guy. Okay, so now, and we define a new random variable, w, and that w is going to be c times y. And I'm reminding you that that c is a constant, a number like 25 or 35. Then what we have seen is that the expected value of that new random variable w is going to be c times the expected value of y. Or using that mu notation, it would be c times mu of y. And again, this is just a lowercase Greek m, because we love our Greek letters in statistics and mathematics in general. Okay, well, that's it for now. Please take care and keep working hard. See you next time. Bye.